I based this video on NEETs module number 5. To download a PDF, I created a link within the video description. Now I will cover alternating current motors. AC motors, they cost less than DC motors. And they do not have brushes and commutators. That means they have less maintenance and they wear less. And they don't spark because they don't have brushes and commutators. They are very good for constant speed applications. Okay. Because the speed, it is determined by the frequency of it. Now, with that, there is the statement that it says, an AC motor can also be made with variable speed characteristics, but only within certain limits. That was true back in the day, and it is true in the fleet today. However, even in the fleet, we're starting to see these variable frequency drives, which I covered at the end, and it is not part of NEETs Module 5, and it's a way to actually change the frequency that you give to the motor, and therefore change the speed. So that's part of the new technology. But for right now, forget about that, and we're gonna cover motors that are AC. We're gonna cover them for polyphase. That means more than one phase, which in the Navy we use a lot of 3 phases, or single phases for very small motors like on reefers. AC motors are divided into series, synchronous, and induction motors. Induction motors are the ones that you will see in the fleet, a lot of them. Now let's talk about the series AC motor. It is an universal motor really, because even though it is wired to work with AC, it can also work with DC. The series AC motor, well, here we got a better picture of it. You see that the field windings are connected in series with the armature windings. Now, this AC motor does have brushes, and this is the only one of its kind, and the field polarity is going to be constantly changing because, well, AC is about electrons moving one direction and then coming back the other direction, and that's going to be causing the polarity to change. In a DC motor, remember the polarity was always, if this was north, that would be south. Now, the speed, as soon as you energize them, and if you don't have a load on it, they're gonna have a really high speed. And then as soon as you start putting a load into it, the speed is gonna slow down. And this is what it means. And here is increasing load, here is increasing speed. So you will find motors like this on drills, portable drills, and the starting torque is very high. That I wanted to point out. Also, universal motors, when compared to a motor of the same size, whether it be an AC or a DC motor, the universal motor is going to be providing less efficiency. Now, the universal motor, it had a brush, but earlier we read that the advantage of AC motors is that they are brushless, so they don't have any brushes. And for that, there is got to be this thing called a rotating magnetic field. That's what makes AC motors so efficient and so maintenance free. Rotating fields may be set up in a 2-phase or 3-phase machines. We'll start with the 2-phase. So here is a 2-phase motor, and if you notice over here, this wire over here, it's connected in series with this wire over here, so this makes 2 opposite poles. That's one pair. And then we got another wire, same idea, connected in series, both of them, to make another pair of poles. And now they put them in one motor, so we got 2 pairs of poles, and what they're going to be doing is, this is going to be north and south, and then after that we're going to have north and south, and so on and so forth, and we're going to have what is called a rotating field. The reason why we want a rotating field is because we're going to have a rotor that is going to be chasing, well, the rotor itself is going to be a magnet, and it's going to be chasing that rotating field, and that's how we're going to get motion. Since you are not going to be dealing with 2-phase motors on the fleet, we're going to skip and we're going to talk about the 3-phase motor. For 3-phase motors, I will have 3 separate windings. As you can see here, I separated them by color code, and then after that all of these are joining into this one, and this is why you are able to get the 3 phases. And there will be 3 wires to where, since the ship's generators will create 3-phase power, that will be three wires. So we're going to be attaching it to the motor so that the motor rotates, and this is going to be a rotating field. Before I talk about the 3-phase motor, let me talk about a little review of what the generator do. So we got a generator over here that provides AC power, and the generator is connected in delta. Bottom line is that, so since it's 3 phases of power, and this is a bus that goes to feed all the loads. By loads I mean motors, pumps, heaters, and so on and so forth, and anything that you can be plug into that bus, to include iPhones and computers and TVs. So we got a motor over here, and that's what the circle represents, and the motor is going to have all the 3 wires, and inside there internally is where it's going to be have all the different connections that I just showed you a moment ago. Now the power that is going to be flowing through those wires is going to be, as you already know, AC goes on a sine wave, and it just changes polarity. So sometimes you're going to have electrons traveling this way, and at the same time that that's happening in that wire, here we will have electrons that are going into the winding and coming out. And then a fraction of a second later, this might have been totally different, okay, to where now electrons are going from here, going to the winding and coming out through here, and then this one over here should, you know, it might be doing something different to where it might be sending electrons. Well, you get the point. It's a total mess of exchange. So at the end, we just simply have different wires that are having, sometimes when this one is rising voltage, like in this case, well, let's see, let me use green for green. So when this one is, the voltage is at the highest, and this wire voltage is at 0. If I'm talking about this point over here. And then if I extrapolate the blue one, it will be somewhere over here, so the voltage over here, it will be at the actually negative point, and so on and so forth. So I took the time and I went ahead and did a few more instances, okay, of the sine waves. Notice how over here, now we got this one over here, and high voltage rising, here more voltage is positive, but here it's actually negative. But a few microseconds earlier, should I say, very short period of time, this was at 0 volts, but this one was rising, and so on and so forth. This changing of constantly polarities within the wire is what we're going to use to have, or to create, that rotating field that I was talking about. Now, to continue what I just was talking about with that AC generator and the sine wave, I got the sine wave over here too. And what I've done is I've taken the time and I have highlighted the highest points of each of the phases. Notice that when one phase is high, the other phases, well, they are neither high, neither low. They are somewhere in between. So by doing that, we can always have a combination of poles that they will have the strongest magnetic field. Like in this one, this time over here corresponds to this time over here. That's why I did the same color. And so the strongest magnetic field, it goes from 1 to 1A pair of poles. The other two are a little weaker, and they are wired so that this is this polarity, or this flux will be leaving and entering this 3A. So if there is a rotor over there that's magnetized, it will be locked onto that. But immediately, a little bit later, now the polarity, the next, in this case, phase number 3 is at the lowest point. So because of that, it's wired so that now the magnets shift very strong, okay, to where north will be here, south will be here. And then remember when I said that I had a rotor over here that was magnetized? Well, that rotor that follows, it will follow and it will try to lock onto that new pole. But then the pole will shift again. So since it's constantly shifting, as the sine wave, as different places, different phases peak, then we accomplish a rotating field, and the rotor that is in the center is going to be always trying to chase that magnetic rotating field, and that is what creates rotation on induction motors. Now, since we are talking about induction motors, well, the key is induction. Induction is the process of transferring electrical power from one wire to another wire without having them touch. So, here we have a rotor that, well, this is the core, and then we got windings on the rotor, and this is free to spin freely. So, as we have a rotating field that is constantly, well, going around where, so what is we're gonna have is the three elements to create power. The rotor has, well, conductor. Then we have a rotating field that is, well, we have a field, and then on top of that, that field is rotating and has certain speed. So because of that, it's going to be a voltage generated. Where? In the center, in these windings. And once that voltage is created there, this is going to get magnetized, because we know that when we got current and flow in the wire, it creates a magnet. So now this gets polarized and has a magnetic field, and it's going to start chasing the rotating magnetic field that is being created by the stator windings. Here we have the stator and the rotor of induction motor, and we do not have any brushes. We do not have slip rings or commutators. That's because the power or the electricity or voltage that is going to be creating here to make this into a magnet, a chasing magnet, should I say, is going to be the rotating field that's going to have here. There are different kind of rotors. We got you can see over there, a squirrel cage rotor, and this other one, the wound rotor. Now, instead of having wire in here, they just simply got slots out of copper, but they accomplish the same purpose as wire. They just really thick wire per se, if you will. Now that I show you this, the wound rotor and the squirrel cage rotor, we're gonna go back to this picture over here. Now, notice that I put some numbers over here, 1200 RPMs and 1100 RPMs. Now, the 1200 RPMs in here, what it is that what I'm trying to say is the magnetic field is rotating at a speed of 1200 RPMs. That rotating field is going to induce a voltage on the windings within this rotor, and the rotor is going to magnetize, and it's going to lock or try to chase as much as it can that rotating field. So this is going to go round it very fast, but it is not going to be able to catch it. That's why I put that it's going to be a lower RPMs, in this case 1100 RPMs. So if I were to subtract from the synchronous speed, which that's what this speed is called, the synchronous speed of the stator, which is the speed of the rotating field. If I take away the synchronous speed from the actual rotor speed, I'm gonna get a difference of 100 RPMs, and that is called slip. So a slip is the amount or the number of RPMs or difference of the rotation between the rotor and the stator windings, magnetic field. Now, a slip is very important because a slip is what allows us to create the voltage in the rotor. Since the voltage on the rotor depends on, well, the amount of windings that is in the rotor times the strength of the magnetic field that it is rotating times the speed of the rotating magnetic field. But since the speed of the rotor is at 1100 RPMs, technically between the rotor and the stator there is only a difference of 100 RPMs, like we learned a moment ago, and we call that a slip. That is what's going to be multiplying here, and that is what's going to determine the voltage inside of the rotor. The greater the slip, the greater the voltage within the rotor. So as we add load to the shaft, the motor is gonna tend to go a little slower, but as soon as that happens, well, the RPMs in here, or the slip, is gonna increase, therefore we're gonna have more or a stronger voltage within the rotor, and that what's gonna do is the rotor is going to have a stronger magnetic field, and because of that, it's going to try to chase the stator rotating winding better, and therefore the speed of the motor is going to stabilize. That's why induction motors are very speed constant. So before I continue, I wanted to show you an induction motor rotor. So this is for a 3-phase motor, and well, here I got, this is a bearing, and I got another bearing over here, and this is the cap holder for the bearings. But most importantly, I wanted you to get the idea that there is no brushes, there is no slip rings in this thing. It's just as an induction field, induction rotor. And here we got, well, the other part of the motor. This is the stator, and we got our windings over there. And in there we got, well, all the 3 phases that I was talking about. Now they are, in real life, they are intertwined. They are not separate like I show you on the picture. That was for learning purposes. Now, going back to well, simple motors, I got back to the single-phase induction motor. So the 3-phase, well, we got 3 phases rotating field, but on the single phase we do not have a rotating field. So as you already know, well, once we connect it up to 110 volts or single phase, what's going to happen is that, well, for the moment this is going to be, we're going to call this phase 1 and cycle 2, or half of the cycle. So on 1, this is going to be north and this is going to be south. Then when it changes polarity, now this will be the south and this will be the north. And it's going to be doing that very fast, at 120 times per second, really, which is 60 hertz. So it will flip around 120 times, and what's going to happen is that the rotor is just going to vibrate, because he doesn't know if to go that way or to go this way. There is going to be a polarity that's going to be induced over here, north and south, but then as soon as this one switches, the polarity is going to switch again. Now the south is going to be on top, the north is going to be here, and it's going to just vibrate. We find these motors on compressors for refrigerators and small water pumps and many other gear. Now, to start them, you gotta get them an initial spin. Once they get going, once you get it spinning, then at that point on, because there is a polarity that's being formed on them, and since they got the momentum going, they will spin forever until you secure the power. Now, to start them automatically, there are a couple of methods. The methods are split phase, and on the split phase we got capacitance starts and resistance starts. The other method is called shaded pole. Right, so I'm going to explain to you first the capacitor start. I got a winding over there, a new winding that was not there before, a capacitor, and a centrifugal switch. To better explain it, we're going to go back to this drawing. So here I got the windings that I had before, and I got my rotor. And then I have added the switch that is meant to open once the motor starts rotating. And then I got a capacitor that is made up of certain capacitive reactance that is going to be bigger than this winding, or greater than this winding. What that's going to do is, it's going to have since the capacitive is going to be a capacitive reactance on this side, current is going to be leading by 45 degrees in this side of the house, in this winding. Now, this field winding, it is a winding, and since there is no capacitors in there, so therefore it defaults to be a inductive reactance. Inductive reactance, they lag current by 45 degrees. Well, now we got this one over here is lagging 45 degrees, this one is leading 45 degrees. So that means that they are 90 degrees out of phase. So what that does is that now the poles are in essence 90 degrees apart. So even though this is pushing and pulling the rotor, because they are creating a polarity within the motor, and the motor doesn't know what to do, this third winding comes over here, and definitely that one is not in line with these other two windings. So since it is offline, it's just gonna push the motor one way, and then once the motor gets rotating, we no longer need this circuit, and that's why the system, it just disconnects itself, and the capacitor and the auxiliary windings, they will no longer get used as the motor starts getting to its final running speed. And that is how an a capacitive start works. The next split phase induction motor is the resistance. And in here, it's similar to the old one. It just has a resistor in series with the inductors. Now, I'm going to go back to this one to explain to you how all that works. So, what happens in here now is that the inductance in here is designed to be made very, very high. Somewhere so that when this is energized, it lags current for about at least 70%. If you make a super strong inductance, the highest you can get is 90%, but 70% in this case will work. And then the auxiliary winding is made of a relatively low inductance, and a strong resistor is put into it. So therefore, this circuit over here ends up having a low inductance. So now current lags only by 30 degrees. But still though, there is a difference between 30 or 70 and 30 of, well, and here I made a mistake. It should have been 40 degrees, and those 40 degrees out of phase, it is enough to make the fields, well, these two fields are going to be pushing and pulling the motor, but this one comes off at 40 degrees later, and it will just spin the motor one way, and once the motor gets spinning, then at that point on, we will no longer need this circuit over here, and same thing as in the motor capacitor starts, this switch will open, and as the motor is starting to approach the terminal speed, and then this system will be disabled until the next time that the motor stops and needs to be started. Then by that time, when the motor comes down to stop, this switch will close again, getting ready for the next start. The last method to start single-phase induction motors is with shaded poles. This is not a split-phase method. So here we got a particular pole, and what they done is they taken on a pole and they wrap a piece of copper in that little part, and that is it. It's not attached to anything. So as voltage starts going up, that induces the voltage in that piece of copper, and that one just causes the natural lines of flux that are going to the other pole to really concentrate in one little corner. When it gets to 90% or 90 degrees of the phase, pretty much there is no current flow, and then what's going to happen is that the little piece of copper now allows all the full flux to go to the other pole, and then as the phase starts to go down, then the field in there starts collapsing, because it has some energy charge in that field, and as it starts collapsing, what it does is that now the lines of flux that are leading from here to the next pole, to the partner pole, they concentrate in that little corner, and then after that, once it gets to zero, there is no current motion, so back again the lines of flux are lying back at the beginning to one side, just like it did over here, and this process keeps going where the field is kind of like pushed up and down, and with that it causes a little fluctuation on the motor, and it's able to start the motor, but it's a very, very weak starting torque. So that's why they only use it for fans, clocks, blowers, and electrical razors. Since we're talking about induction motors, well, there is a special induction motor called a synchronous motor. Synchronous motor is called because it runs at the synchronous speed. Remember, synchronous speed is the speed of the rotating field, and the motor runs at that same speed. It does have, as you can see, two slip rings, and what they do is they bring AC to the rotor, and what it does is it makes the rotor to act like a magnet bar, very strong, and because of that, this motor is able to keep up with the rotating field. And in this motor, well, we do not need induction really, because we don't need a slip, because we already got power to create a very strong magnet in there. But this motor, as it is, it's not able to start by itself. To be able to start by itself, it needs to have a squirrel cage winding, and that one is one at the edges, and once they energize it, what it's going to do is it's going to bring the motor to the rated speed, or near the rated speed, and then at that point on, that's when they energize the brushes, the slip rings, and then at that point on, that's when the motor locks onto the synchronous speed. Once synchronous motor speed is up to the synchronous speed, they can rotate heavy loads and not lose any speed. They can also be used in the certain conditions to correct the power factor when you have too many inductive loads. Finally, we need to talk about the variable frequency drives. Here we got variable frequency drive 1 and 2 because they go to two 3-phase AC motors. And variable frequency drives. So these variable frequency drives, what is so good about them is that they can take a regular AC 3-phase power at 60 Hertz, and then they will change the frequency. And if you remember, or I don't know if I went over it, the formula for the speed of the motor is the speed, which is N, is equal to 120 times the frequency of the power coming in times the number of poles. This will determine what the speed of a motor is. So all of our motors are designed to be at 900 RPMs or 200 RPMs, and they are already set for 60 Hertz. If you take one of those normal motors and then you hook it up to a variable speed drive, and if the speed drive changes the frequency, by changing the frequency, it's going to change the speed of the motor. Now, to better explain a variable frequency drive, so we got a motor over here, and this over here represents the variable frequency drive itself. Power comes in, and it's get taken to these rectifiers, which what they do is they converted the 3AC power into DC. So over here is only direct current, and then they take certain, in this case, these look like transistors, but they are actually MOSFETs. And these MOSFET transistors, what they do is they flash in a sequence that they will basically invert, and that's what they call this an inverter. An inverter is a device that converts DC power into AC power. So once we get the power over here, we're still gonna get 440 volts, but now, and it's still gonna be 3 phases, but the frequency is gonna be anywhere between 20, 30, 40, or 80 hertz, and what that's gonna do is it's gonna change the speed of the motor, so we can really literally have this motor rotate, if we want to, at 1 RPM per minute or 20 RPMs. We see these motors, or actually in the future, we're gonna see them more and more. Now, where you're gonna see them as soon as you walk in the ship, even if it's an old ship, it will be the lathe. A lathe is a particular machine that the MRs use to cut pieces of metal, and the lathes, they need to be able to run at multiple speeds, and they use variable frequency drives to be able to adjust the motors to that particular speeds. And when you look at the motor, it's just going to be a regular 60 hertz motor that it just has this frequency altered. The new type of ships, the propulsion system, the ones that they say direct drive systems, they also use gigantic variable frequency drives.